When the electron in a hydrogen atom moves from n equals 6 to n equals 1, light with a wavelength of blank nanometers is emitted. Draw the electron transition. So we need to draw the electron transition and we need to solve this question, and we want to know how many nanometers of light are emitted. So the first easy part is to draw the electron transition. So we want to start on the n equals 1. And so then we kind of can draw the rest of these. So n equals 2, 3, 4, 5, and 6. So we know that n equals 6. And so it moves from n equals 6 to n equals 1. So we can draw an electron that transitions from n equals 6 to n equals 1. Okay, so part 1 done. So the next part asks us to calculate the wavelength of light. And so we need to be able to manipulate some of these equations. But we know that we can calculate the change in energy between these two, and we're pretty sure that that's going to be related to the energy of the photon of light. Okay, so delta E between these two is going to be negative 2.18 times 10 to the negative 18 joules, 1 over nf squared minus 1 over ni squared. Okay, so now we can plug in the values that we have here. So negative 2.18 times 10 to the negative 18 joules, 1 over 1 squared minus 1 over 6 squared. Okay, when you plug this into your calculator, right, initial, final, we get negative 2.119 times 10 to the negative 18 joules. Okay, so the question is, how can we use the change in energy between these two states to determine the energy of the photon, which is related to the wavelength of light? So what we need to remember is that delta E, or the absolute value of delta E, is equal to E photon. Okay, and so these two values are essentially the same. And so E photon is equal to H Planck's constant times the frequency. Okay, we still haven't quite gotten to the wavelength of light, but if you remember that the speed of light is equal to the wavelength of light times the frequency, so we could resolve for the frequency, that the frequency is equal to the speed of light over the wavelength of light. So now we can plug that into this, where we have hc over lambda. Okay, and so all we've done here is manipulate equations. So if we would like to solve for the wavelength of light, the wavelength of light is going to be hc over E photon. And don't forget that E photon is equal to the absolute value of delta E. Okay, so now we can plug this in to solve for lambda. So lambda equals hc over E photon, where h is Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds, multiplied by the wavelength, or the speed of light, which is 2.998 times 10 to the 8 meters per second, divided by the energy of the photon of light, or delta E, which in this case, the absolute value of that is 2.119 times 10 to the negative 18 joules. If we look at our units, we're going to end up with something in meters, but the question asks for it in nanometers. So I'm going to go ahead and do that conversion here. So in 1 meter, there are 1 times 10 to the 9th nanometers. Okay, so we can plug this into our calculator. So lambda is going to equal 93.7 nanometers of light. Okay, so let's go over this again. So we calculated the change in energy between the two states. Once we got that, we remembered that the absolute value of the change in energy is equal to E of the photon. Okay, and then we know that E photon is h times the frequency, where h is Planck's constant. So we still need lambda, and so you can either solve for this and then rework, or you can manipulate your equations where the speed of light is the frequency times the wavelength. So we can solve for the frequency, which is the speed of light divided by lambda. We just plug that into this equation and then resolve for lambda, where lambda equals the speed of light times Planck's constant over E photon, and then we plug that in to get this answer.